science, mathematics with Sunday Oluwafemi. I'm a PhD student from the Department of Mathematical Science, Indiana University, Indianapolis, USA. So, in this playlist, I will be going through measure integration and Riemann analysis. Specifically, we'll be using textbook by Sheldon Axley. Okay, so you can get this textbook online on his page. Just type on measure theory, measure integration and Riemann analysis by Sheldon Axley on Google. Search, then you're able to have free access to this textbook. Okay, so we'll be going to the chapter 1 of the textbook today and see how far we can go. So the first review we're going to do will be on Riemann integration. So these brief chapters will use Riemann integration, and Riemann integration uses rectangles to approximate areas on the graphs. These chapters begin by carefully presenting the definitions leading to the Riemann integral, and the big result in the first section states that a continuous real-valued functions on a closed-bounded interval is Riemann integrable, and the proof depends upon the theorems that continuous functions on closed-bounded intervals are uniform continuous. But before we move on, we'll begin with a few definitions needed before we can define the Riemann integral. So, in our definitions throughout, we'll be using, we let our R to denote the complete order field of real numbers. Okay, so let's check the fixed definition. I got that 1.1 definition. So the definition we'll be checking is partition. So we have suppose A, B belongs to R with A less than B, then a partition of A, B is a finite list of the form x0, x1, x2, xn, where A equals to x0 less than x1 less than less than xn equals to b. So these are the key things to take note in this definition of partition. So the basic idea is that we have a line, so bounded A, and then we choose to divide this line, and that is what we mean by the word partition. Then we divide to partition this line. So we pick this point as to be x0, and this is x1, x2, x3, x4, x5, and this will be our xn, depend on the nth times of partition you have. So in other words, we can write this as a comma b equals to x naught x1 union x2, union x1 comma x2 union dot 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 union xn minus 1 comma xn. Okay, so for an example, let me just give a simple example so that we can move on to the next definition. Example, we have 0, 4. So we can partition this our closed interval 0, 4. We can choose to divide it into 4 or to 3 sub interval. So then we can have this to be our x naught. Then we can have this point, and it's okay. Let's make it bigger. 1, 2, and then 3. So then we have this to be our x1. Sorry about this. So we have this to be x2, to be x3, and this to be x4. Then we can now write the interval based on the partition 0, 4 to be 0, 1 union 1, 2 union 2, 3, and finally union 3, 4. So that's just the basic simple intuitions about partition. So the next definitions we'll be considering, call that 1.2. Definition, that is notation for infimum and supremum of a function. So let's check the basic definition. So if f is a real valued function and then a is a subset of the domain of f, then our definitions of infimum f over the subset a equals to infimum, which is f of x such that x belongs to a, and sup f over a is equals to the supremum of f of x such that x belongs to subset a. So with this definition now, we can now define our lower Riemann sum and upper Riemann sum. So let's check the definition before we check the intuitive meaning of it. So let's say we have suppose we have our function f over our domain b to r is a bounded function, and then we have our partition P x naught dot 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 xn of a comma b. So the lower Riemann sum so we are going to denote that as L, the function f, the partition p, and the domain a comma b is defined to be equals to summation j equals to 1 to n, j equals to 1 to n. That is our maximum partition we picked here. So another thing to measure too, you have to be very careful of your notation. So then we have xj minus xj minus 1, and then infimum f, where sj minus 1 sj. So then the second definitions for upper Riemann sum. The upper Riemann sum is u fp a comma b. So defined, just changing the infimum to supremum. So let me have it this way. J equals to 1 to n sj minus sj minus 1 sup f over sj minus 1 sj. So intuitively, let's say for example, we define our f over 0, 1 to l by f of s equals to s squared. So we have the function to be of this form. Okay, so the upper Riemann sum, moving between 0 and then 1. So we have our range here, it's to be 1. So our lower Riemann sum, NFP, it just tries to approximate our function from below using rectangle. So this is our lower Riemann sum. So we are trying to approximate the function x squared by rectangles from below. So that's our lower Riemann sum. So then our upper Riemann sum is just trying to approximate the function from above. Then with that we are able to get the area under this curve x squared. So if you notice, you see that our upper Riemann sum is above the graph. So that is our upper Riemann sum. So we tried to approximate the function first using lower Riemann sum to approximate it from below, then using the upper Riemann sum to approximate it from above, so that we're able to get the area under this curve successfully. So that is the definitions about that. Then the next thing is to check some basic theorems. Got that 1.5. So okay, we have inequalities with Riemann sums. So we have suppose f ab to R is a bounded function and p, p prime are partitions of AB such that the list defining P is a sublist of the list defining P prime. Then these inequalities hold. The lower Riemann sum of P over P is less than the refined lower Riemann sum partition, and it's less than upper Riemann sum F P prime A comma B. And this is less than the lower upper Riemann sum of P AB. So what this means is that if we refine our partition, for example, if we have our P, this is our AB, so we have our P to be this red line. That's our P. Then we have our this they call it now this black partition. So to be our P prime. So you notice that our P prime is more refined than our P. So the lower Riemann sum in this respect, is less than the lower Riemann sum when it is more refined. That is, if we have a finer partition, the lower Riemann sum increases, but the upper Riemann sum, if you notice here, the upper Riemann sum reduces. So if we check the previous example, for example, we have the function to be this our x squared. So if we have a big partition, so the result you will get with this partition will be less than the result you will get for the lower Riemann sum if you refine your partition. The more we refine our partition, the more the lower Riemann sum increases. But it is other way for the upper Riemann sum. The more you refine your partition, the more your upper Riemann sum reduces, but your lower Riemann sum increases. So let's check the proof of this theorem. What we want to prove is that if P prime is if P is a sublist of the list defining P prime, then LFP A comma B is less than LFP prime A comma B is less than LFP prime A comma B less than upper Riemann sum FP A comma B. So this is what you want to prove. Let me put the proof here. Okay. So let's see. So to prove the first inequalities, let's start from this point. We have suppose P is the partition x naught x1 dot dot xn, and then P prime is the partition we have x naught prime x1 prime dot dot xn of A comma B. So for each j that belongs to 1 dot dot n, you have there exists k that belongs to 0 dot dot n minus 1 and a positive integer m, such that sj minus 1 from this partition, from that partition. So we have sk prime less than sk prime dot 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 less than sk plus m prime equals to sg. So with that we have sj minus sj minus 1 infimum f sj minus 1 sg equals to summation I equals to 1 m sk plus I prime minus sk plus I minus 1 prime infimum f sj minus 1 sg, and then this is less than or equals to summation I equals to 1 m sk plus I prime minus sk plus I minus 1 prime infimum f. So the change is this interval. This infimum is not over the finest partition. which is sk plus I prime over sk plus I prime. So, and this inequalities implies, and this implies our Riemann sum of fp a comma b is less than the lower Riemann sum of fp prime a comma b. So here we have this, and then from here we have this. So the same way we can also check for these other two inequalities. Then we have that result. So another definitions that we need in order for us to able to define Riemann integral is the relationship between the lower Riemann sum and the upper Riemann sum. So we have this theorem: the lower Riemann sums is always less than or equals to the upper Riemann sum on the same partition. So we have, suppose f a function on a comma bit to r is a bounded function, and then p prime are partitions of a comma b, then this inequality holds. Now the lower Riemann sum fp a comma b is less than the upper Riemann sum of fp prime a comma b. So let's share the proof of this also. So proof. So let's divide a new partition p prime prime will be a partition of a comma b, and this p partition is obtained by taking the union or merging the two partitions together. So then we have our lower. By the previous theorem we have proved, we know that this p prime prime is more refined than this, then this will be less than f p prime prime a comma b. Why? Because this partition is more refined than this, so their inequalities holds. Also by the same theorem, which is theorem 1.5, these inequalities also follow N, so the upper Riemann sum of the refined partition, and then this is also less than, by the same theorem, fp prime less than b. Then we have our desired result: the lower Riemann sum is less than or equals to the upper Riemann sum over the same interval a comma b. Okay. Next by theorem 1.5. So next definition. That will be 1.7. So we will define the lower sum and upper Riemann integral. Sorry, lower and upper Riemann integral. So suppose we have our function f and ab is to r. It's a bounded function, always bounded function. So the lower Riemann integral so denoted as LFEP. So this does not have a partition. And then the upper Riemann integral so also denote this as UF and the interval alone. So we define these two definitions as the lower Riemann integral a comma b is equal to the sub over p of the lower Riemann sum, and then the upper Riemann integral is given as infimum over p, the upper Riemann sum. So where the supremum and infimum above are taken over all partitions P of A, comma B. So in the definition above, we take the supremum over all partitions of the lower Riemann sum, and then by taking that, we are able to approximate the function appropriately, and then that will give us approximate or accurately estimate of the area under the graph we are checking. Okay, so with that now, then we need to check the relationship between our lower Riemann integral and then our upper Riemann integral, so that we have 1.8 so lower Riemann integral is always less than or equals to the upper Riemann integral. So we have suppose f a comma b extends to R is a bounded function, then this inequality holds, and f a comma b is less than the upper Riemann integral. So this is actually followed by the definitions of 1.6. You can actually go through that as an exercise. Now we can now define our Riemann integral. So that will be definitions 1.9. We have Riemann integrable, and then Riemann integral. So a bounded function on a closed bounded interval is called a Riemann integrable. If it's lower Riemann sum, if it's lower Riemann integral, equal its upper Riemann integral. Okay, so we have if f a comma b thanks to R is Riemann integrable, then the Riemann integral AB of f is defined by integral AB f equals to lower Riemann sum f a comma b, and that is equals to the upper Riemann integral a comma b. So that will be our basic definitions for Riemann integral, and then we'll be making use of it to check some problems, some solutions to some certain problem. So now we have another theorems that we need to take note, and that is continuous function, continuous functions are Riemann integrable. So we have every continuous function with valued function on each closed bounded interval is Riemann integrable. So let's show the proof of this using the definitions of uniform continuous. We have proof. Let's suppose a comma b belongs to R, and with a less than b, and then we have function f a comma b to R is a continuous function. So we know from our standard theorem from undergrad ring analysis, f is bounded and then is continuous. So let epsilon be greater than 0. So since f is uniformly continuous, so we have the exist a data greater than 0 such that we have f of x minus f of t, the mode is less than epsilon, that is for all s comma t that belongs to a comma b, and then the mode of x minus t is less than delta. So we have that by definitions. So here let n be positive integer, so be sure that we have this interval equal interval over n. So we need to define our partition. Let P be the equally spaced partition. A equals to x naught x1 dot xn, which is equals to b of a comma b. So with the distance of each sub-interval is equals to b minus a over n. This for each j equals to 1 to n. So then, by our definitions, the upper Riemann integral minus the lower Riemann integral is less than the upper Riemann sum minus the lower Riemann sum so, and this, since they will have the same length, but the difference, okay, this by definitions we have, this is our length, which is b minus a, or by definitions we have these guys to be summation j equals to 1n, and then we have xj minus 1 and sup f over sj minus 1 sj, and then by definition we have the lower Riemann sum is to be j minus 1n sj minus 1 infimum f sj minus 1 sj. Then by the way we define our partition, we have this, for each of these guys we have b minus n, so then we can factorize these two out. So we have b minus a over n, then we are left with summation j equals to 1 and the sup f over sj minus 1 sj minus infimum f sj minus 1 sj. Okay, so by our definitions we have these two guys. By definitions of continuous functions, we have these two guys to be less than epsilon. So then we have b minus a over n so taking the sum of this, we have this guy to be less than n epsilon. So the summation over this guy we have n, and then these two guys we have epsilon. Let me make it more clearer. So we have these two less than epsilon, then with this n, so we have this n, because if we take the sum of this we have this, so with that we are going to have this to be equals to b minus a epsilon. Okay, so since this is b minus a, and then for all epsilon greater than 0, so we have shown from so far that the upper Riemann integral, a comma b minus the lower Riemann integral is less than b minus a epsilon for all x(n) greater than 0. Thus by theorem 1.8, so thus by the theorem 1.8 we have proved we have our upper Riemann sum is equals to the lower Riemann integral. So hence, since these two are equal, hence f is Riemann integrable. So this follows from the definitions. Okay, so the last thing we are going to check in this sessions 1a before we check solution to some selected problems, so is bounds on Riemann integral. So how can we bound our Riemann integral? That's bounds on Riemann integral. So suppose f is a comma b to R is Riemann integrable, then this inequality holds b minus a, the length of the interval, infimum over a comma b, f is less than the Riemann integral ab, f less than b minus a, sub f a comma b. Okay, so this is the bounds on our Riemann integral, the lower and then the upper bound. So let's prove this theorem. So let's define our p. Let p be the trivial with trivial partition. We're just taking our a equals to x0, which is less than x1, which is equals to b. Then by definitions of the lower Riemann sum, we have b minus a, which is already the partition we have, then the infimum f over a comma b. That's the definitions of our lower Riemann sum. And we know that our lower Riemann sum is less than our lower Riemann integral because this has to do with the sup. So, and then this is equals to ab of f. So that's we have proved the first side of the inequalities. So in the same way we can prove the other side. So similarly, b minus a sub f over a comma b. This is the definitions of the upper Riemann sum. And then we know that this is also greater because the upper Riemann integral have to do with the infimum. So the upper Riemann sum is greater than the upper Riemann integral. So we have these odds. And then this is also equals to ab of f. So we have that. So we have proved both directions. So simple to understand. So yeah, I will stop this video here. Then the next video I'm going to give solutions to some selected problems in this sessions 1a. So I just urge you to like the videos and then also subscribe and share it to fellow graduate students. Thank you.